In this video, we're going to look at a concept that we call concavity and another one which we call points of inflection. So what concavity and points of inflection have to do with is the shape of a graph. So we're going to consider these two graphs here, both with points A and B. So one graph is going to connect points A and B like this. I'll call this one f of x. And the other one is going to connect points A and B like this. So notice that in both cases, f and g are increasing because they go up as you go from A to B. So that means their first derivative is positive since it's increasing. But the sort of shape or way in which the graphs increase is different, right? It's sort of bent differently. And that has to do with what we call concavity. So I'll just define it quickly. This one we call concave up. And this one we call concave down. Now what does that mean, concave up and concave down? Now you can look at it and kind of see the direction that it's going, and that's what concave up and down will mean. But it's going to be related to the tangents or to the derivative. So notice that if we were to draw the tangents or some tangents to this curve, tangents would look something like this. Now obviously the tangents here all have positive slope because the function is increasing, and the tangents for g would also have positive slope. But there is something different about the tangents. In this case, for f, the one that we said was concave up, the tangents were all below the curve. So the tangents are below the curve. And for this one, g, which we call concave down, this one, g over here, which is concave down, the tangents are all above the curve. And that's how we'll define concave up and concave down. So concave up means tangents are below the curve. Concave down means tangents are above the curve. Now, another way to think about this, like you probably don't want to have to draw the tangents every time. Just think about parabolas. Think about a parabola which is opening up and a parabola which is opening down, right? So we already have that terminology from our knowledge of quadratics, opening up and opening down. Well, a parabola which is opening up, if you were to draw the tangents, I missed there. If you were to draw the tangents, they're all below the curve. You know, even though it's decreasing here, the tangent's still below. And for one that's opening down, the tangents are all above the curve. So opening up is the same as concave up. And the same for opening down. Is the same as concave down. So you could kind of think of concavity, concave up and concave down, as kind of a generalization of that idea with parabolas of a parabola opening up and opening down. But concavity is going to apply to different types of functions. So, you know, as a quick example, consider a cubic. We'll just go with that parent function y equals x cubed. That function looks like this, and you couldn't say, you know, it's opening up or opening down. It's actually kind of doing both, and now we're going to talk about the concavity. If we took values less than 0, so if x is less than 0 in this example, then the tangents would all be above the curve, right? So in that case, it's concave down. And if x is bigger than 0, you were to draw the tangents over here, they're all below the curve. So in that case, we'd have concave up. Okay, so this graph, this cubic, we actually see that we have both concave up portions and concave down portions. And actually, this point, x equals 0, turns out to be a pretty important point too, because this is the point where we kind of switch. It switches from being concave down to concave up. A point where you switch concavity, that's actually a special point. We actually give that the name. That's called the point of inflection, or an inflection point. So the definition of a point of inflection is a point where the concavity switches. Or changes. So i.e. for y equals x cubed, 0, 0 is a point of inflection. Okay, so that's our definition of concave up and concave down. Now what we're going to want to do is figure out how do you actually determine, let's say if we looked at the graph, let's consider that parabola which is concave up and that parabola which is concave down. How am I going to figure out, let's say without actually looking at the graph, hint, relating it to the derivative if I have concave up or concave down? Remember that in that first example, knowing that the function was increasing didn't tell us the concavity. But what I'm going to do here is I'm going to draw the tangents. So this one's clearly concave up, right? We know this one's concave up because if I were to draw the tangents, they are all below the curve. Missed there. But what's happening to the tangents or the slope of the tangents as you move from left to right? So notice here we have a negative tangent. Here, still negative, but not as steep, so the slope is smaller. Over here, the tangent is now positive. As I go further to the right, the tangent is more positive. So as you go from left to right, the slope of the tangent is increasing. So let's think about what that means for the derivative. Therefore, so the slope of the tangent is increasing. That means f prime is increasing, because that's f prime is the slope of the tangent. But if f prime is increasing, that means its derivative, the derivative of f prime, is increasing. So the derivative of f prime is increasing. If the derivative of f prime is increasing, therefore the derivative of f prime the derivative of f prime is not increasing. The derivative of f prime is positive. Right? That's what it means for that's what it means for the derivative to be increasing. The derivative is positive, but the derivative of f prime is f double prime is positive. So a function is concave up if the second derivative is positive, or it's concave up whenever its second derivative is positive. And then the opposite thing would work for concave down, right? Tangents are all above, but in this case, the tangent's what's happening to the slope. Well, it's positive, less positive as we go to the right, becomes negative, and even more negative. So for concave down, slope of tangent is decreasing. Which means derivative of f prime is negative, which means f double prime is negative. So this is going to be our test. The function will be concave down, or when the function is concave down, f double prime, or the second derivative, will be negative. And it will be concave up if the second derivative is positive.